chapter 5. Try to get through this chapter through this week, okay? And as we talk about it, you are going to have, your test start today. So when you are done with your test, we have a quiz for and the final. So we try to finish almost everything by the end of this week. So we give you a quiz, 6 questions on the quiz would be coming from this chapter 15, and it's going to be repeated on the final. Okay, so final, as I talked about it, you are going to have 12 questions. There's going to be 6 from this quiz and the concept of chapter 5, and 6 or 7 from the chapter 14, which is integration. Okay, so we continue with the function, the vector fields. Okay, so let's go through this one. We are going to introduce a new concept of integrations, quite interesting one. So this new type of integrals is the one that you use in science, okay? Measuring physics or others. If you'd like to take advanced calculus, or if you're going to be math major, you are going to read so-called advanced calculus using the complex variables or the complex functions. When you go to the complex functions, complex analysis, this is again the type of integral that we're going to use, okay? So it would be 15.2. So that would be Monday, 24, 23. Okay, and we're going to talk about, that's a 15.2. We're going to talk about the line integral. Okay, line integral is mostly the one that we use in science. Okay, and that will take us to the integral when you want dealing with those vector fields. Okay, remember the vector fields are function of 2 or 3 variables it's going to be defined into R2 or R3. So it's a vector valued function of the 2 variables or 3 variables. Okay, so let's see what we're going to do. You see, in calculus 1, or the function of 1 variable, we go back to definition of integral again. So what do you do on those? We define the definite integral. Definite integral is going to be, we define the definite integral on a closed interval. Your closed interval is going to be a segment of the line. So we just talk about it when going from point A to the point B. And the way we do it, you know that we do those partitioning one and the Riemann sum. So we are going to stay in that line, if you like. But what we are going to be consider is we are going to travel on a curve, if you like. We travel on a given curve, and we are going to do the same thing, if you like. So let me just, as we go on, I'm going to build up what we did before, step by step. The construction is important for us. As soon as we do it, the result's going to be easy formula. But we make sure that we understand it and how we're going to construct a new integral. Okay, so let's start with what we know once more. Okay, once more, recall the Riemann integral. Okay, so recall that, you know, that if a function is defined on a closed interval, if a function, if a function f is defined on a closed interval a and b, it's a real valued function to r, is so-called integrable or Riemann integrable in a sense of the function of 1 variable, okay, which means you can partition, you know that you can partition between a and the b and put your integral, and this is going to be your integral a to b f of x d of x, okay, and is equal to the Riemann sum, which is going to be the limit of the Riemann sum sigma of f of let's say ci or xi star, as we do it in this case, times delta x. Okay, you can say delta xi, it doesn't matter. I from 1 to n, when n goes to infinity. So that was the idea of the integral. And of course, if this is going to be a positive function, this can be considered as the area under the curve. So if f of x, okay, so if f of x is going to be greater than or equal to the 0, is positive, okay, is a positive function, okay, positive function, and then of course an f is continuous, and f is going to be continuous on the domain that we have, which is a closed interval of a and b. Then the interpretation of the integral is going to be area under the curve. Then a is equal to the integral from a to b, f of x d of x is going to be the area, okay, area under the curve or under the graph, okay, under the graph, under the graph of y equal to the f of x from okay, from x equal to a to x equal to b. This is what we know so far, and we'd like to extend it in a okay new format, if you like. Okay, so you know that the construction for this one, this means this is going to be the construction that we have. And this is going to be our curve. Okay, the function is positive, so the curve is going to be above the x-axis. So what we do, this is going to be the interval of the a and the interval of the b. And the way we do it, remember, we just divide this one into equal parts, if you like, or any partition. So this is the situation that we are going to have. And then we find the area of these rectangles, and we estimate the area under the curve. So the situation is that we got this partitioning of the closed interval, a and the b, okay? And we do this partitioning, equal parts or otherwise. So I want to do extended similarly. So let's spend a little bit more time to construct it. So the partition that we usually start, this is going to be x0, and this is going to be the x1, x2, x3. Then you go to the xn, which is equal to the b. So the idea is finding the area under the curve means finding the area of each of these rectangles. So what we do, we go to each interval and we pick a representative. Okay, in this interval, we pick a point, we may call it x1 star. So it's going to be any number between a and the x1, because any number would do it, so that they give you the, okay, this length is going to be the delta x, and then we would like to find this portion, which is going to be the height. So as soon as you pick the point, you bring it down, and that give you f of x1 star. Okay, then you multiply this one by the delta x or delta x1, doesn't matter. Okay, you multiply by the length of that interval, depends how we're going to make it. So that would be the area of the first one. Okay, so we do the same thing to the second part, and we pick another number and we call this one x2 star. And then we can continue. We can continue here doing all this operation. We may get to the I parts or I position. So we pick the point in general on xi star. So we drop it into the function to get f of xi star. And then that would give us the area of that rectangles, okay, the I parts. The first, the second, the third, the fourth, the fifth, and then we continue. Okay, as we continue, you know that this is it. So we put them together, that give us the limit. Okay, then we do just the area, if you like. The area in question is going to be approximately that sigma of f of, okay, xi star times delta xi, I going from 1 to n, of course, when n is large. So that's the idea of the definite integral or the Riemann integral, okay, to get these numbers. So this is what we know so far regarding those functions. Okay, now let's switch it. So what we're going to do is we are going to start it again, but this time the function is going to be a function of two variables to start with, okay? It's going to be a function. The function would be a function of two variables. Okay, when the function is going to be a function of two variables, so the way we are going to do it, we are not going to get the graph of the function to be write the graph of the function because it doesn't make sense to get this type of ideas. So what we're going to do is we are going to have that interval of a and the b. Then what we do is we are going to consider a curve, a smooth curve. You know, go from point A to the point B. We are going to go from point A to B along a curve, if you like. Okay, that curve would be given to you. A smooth curve, you know, that would have an equation, r of t. So you know that your function is going to be defined on a closed interval, but the range of the function is going to be in R2. Then you are going to be kind of compose them to the given function, and we would like to do the same thing all over. Okay, so what I'm going to do is I'm going to take this one and put it into the two-dimensional version. And of course, when you extend it, when you want to do research, so you may have to modify some of those results that you already have. So what I'm going to do, okay, so the way we did it, you see, you go from point A to B really on a straight line. This is the way we do it. So what we're going to do is there's going to be a curve involved. Okay, so let's put it into a two-dimensional version and see if we can find something similar. So start it over. To start it over and say, okay, now we bring a curve first. Okay, that's going to be the curve. So suppose this integral depends on the path that you're going to have. Okay, for example, you want to go from here to San Diego. So you have different paths to go. You can go through the 15 or can go through the 5. Okay, so this is going to be a situation they're going to have. Then we'd like to find the measure, the distance that you're going to have. So suppose C is going to be, I bring a curve, capital C is a smooth curve. Let me talk about it. You know, the equation is, okay, it's going to be differentiable and derivative never zero. Suppose C is going to be a smooth curve. We start in R2 first, then we extend it to the R3. R2, okay, with the parametric equation, of course, with the parametric equations. So this is going to be the parametric equation as we talked about the other day. So your x is going to be a function of time, which is going to be x of t. At different times, you are going to have different places. So it's going to be x of t. Then your y is going to be y of t. Okay, then your t is going to be between a and b. So you're in two-dimensional. At different time, you're going to be at different point. Then we can extend it to the three-dimensional. And then equation can be written as r of t is equal to, in the coordinate format, it's going to be x of t comma y of t. Of course, we can write it down as x of t times I plus y of t times j. And your a is going to be between, t is going to be between a and the b. Okay, so I bring a smooth curve. Now I bring the function. But my function this time is going to be a function of two variables. Okay, so there you are. So if you have a function, if f is, let's say if f is is a function, okay, it's going to be a function of two variables, function of two variables. going to be two variables. So let's say X and Y. So let's see what is going to be a situation that we did have. So what we're going to do, we are going to do the same procedure that we did it for the other one. So this is going to be our graph so far. So you see, this is going to be the one. So you have this smooth curve that we talk about it. So this is going to be the curve. Okay, suppose this is going to be your curve. So this is going to be the curve C in two-dimensional. Okay, that's the one. Then the situation they're going to have is when you want to travel from A to B, okay, when you want to travel from the A to B. So the situation that you are going to have is going to be at the, so what we do is we partition again, you see, if you partition the A and the B on the number line that we're going to have, then you get different points. You see, we partition this one into different points. So suppose this is, because this is going to be the kind of initial points. We call this one P0 if you like. Then I have this point, I call it the P1, then the P2, P3, and I keep going to get to the Pn. Okay, so what I would like to do is I would like to travel, if you like. If you would like to travel, so the situation is going to be this one. You see, it's going to be the situation we're going to have. This is going to be the domain of the curve, which is going to be from A and the B. Okay, so I partition this one in terms of the time. Okay, I partition this one in terms of the time. So this is going to be at the time 0. It's going to be at the time 0. This is going to be the first T1, T2, T3 to the Tn. Okay, so at the different times, I'm going to be at different position on the curve. Okay, when you travel, the situation you're going to have. Okay, so for example, if you are going to be at the time, let's say, so this is going to be the situation they're going to have. You see, you get the T here. You get the T at the time T, you are going to be at a point. So what's going to be the coordinate of your point? The coordinate of the point is going to be X of T and Y of T. This is because of the function that you have, okay? The function, which is the function R. Okay, so what we are going to do, we are going to do something similar to the one that we did, okay? So look at this one. So the situation that I have is, this is going to be the one again. This is going to be A and the B that I have. I'm going to partition this one, see, respect to the time, T0, and this is going to be the Tn. Then I have, again, I can have the equal one or otherwise. So again, I partition it into some sub-interval. So that give me a situation at different time. So this is going to be, again, the T1, the T2, the T3. Okay, and just keep going, giving to the 3n. So what I'm going to do is, you see, the points that corresponds to these are going to be the P0, P1, P2, P3 to the Pn. So at different times, I'm going to be at different points on the graph of the C when I travel. So what I'm going to do, I'm going to do the similar thing that we did for the other one. So in this, I pick a time between these T0 and T1, at a specific time. So I can pick any time I like. So I'm going to pick the first one. Again, I'm going to call this one, okay. I call this one Ti star, if you like. Okay, anytime. When I pick the Ti star means I'm going to be somewhere here, okay? So this means I'm going to be at the point. So that point I'm going, sorry, that's a T1. So that's it, to start with. To start with, it's going to be T1 star. So at the T1 star, I'm going to be between these 2 points. So the point that I'm going to consider, I'm going to call it P1 star, okay, at the point B. But this point would have a coordinate. So what's going to be the coordinate of this point? It's going to be X and Y. So how am I going to find it? I have the function here. So the coordinate of this point is going to be X of T1 star, okay, and the Y of the T1 star. Okay, that's going to be the one. So what I'm going to do later, then I can drop this one into the function, if you like. Okay, I can drop it into the function, If I drop it to the function, you know, the function is a function of two variables. So I'm going to get f of, okay, x of t1 star, comma, y of ti star. Okay, so that gave me the value of the function. So what I would like to do is, I would like to get that delta x that we did. You see, in the previous case, the delta x was what? The delta x is this segment. It's a distance. Okay, when you multiply, it's going to be a distance here. But if you want to consider the distance that you travel when you do the function of one variable, the distance is going to be going from A to B. So the distance is going to be delta x, this segment. But when you're dealing with this function, then you consider you're traveling on the curve. If you're traveling on the curve, okay, instead of a distance, because it's a curvilinear. You see, when it's a curvilinear, if you want to find the distance between these 2 points, you know that the distance in that case is going to be what? It's going to be the arc length. So it's going to be the arc length of the, okay, small part, if you like. So what I'm going to do is, I'm going to pick this point, then I multiply by the arc length. So this is going to be f of x of t1 star, comma, y of t1 star times the arc length of the, okay, of the first part. Then I'm call it delta S1. Any question? So you cannot talk about the delta X, doesn't make sense, or the one we would like to create. So if you copy the one that we did, okay, if you copy the one that we did, so we are going to have something similar, okay? So, you know, it's going to be a T1, then you can pick it in some values like a TI star. So we do the same thing, okay? There's going to be another one, another one, another one, and somewhere over here, you may pick something like a TI star, okay, and do the same procedure that we did over here, okay? Then, so this is going to be a situation you're going to have. Now, if you put them together, so what is going to be the case that we are going to have? You see, if you put them together, previously the result, we call it area under the curve, and we call it integral. So in this case, if you want to pick something similar, the similarity is going to be, remember, this is going to be the sigma. Okay, sigma of those quantities that we pick is going to be f of, okay, x of ti star, comma, y of ti star, this quantity that we pick over here. Okay, then this is it. You multiply by the delta xi. Delta xi means the differential or the change in the arc length. Change in the arc length, which is going to be I is equal to the 1 equal to the n. Okay, so that would be the sigma that we talk about it. And if you take the limit, okay, if you take the limit when these portions are going to be very small, or just partition it over and over and over, when n goes to infinity, okay, when n goes to infinity. So this would mean something for you. If you want to copy the one that we did before, you see, if you want to make a copy that we did before, so this must be a kind of integral. You know that the way we create the integral, the function is going to be the function, but this ti star, xi star that we talk about it, okay, these are going to be changed to the what? Okay, this is a point, so it's going to be kind of f of x comma y. Okay, that's going to be the one. The differential, we usually have delta x and we call it dx. In this case, you have a differential of the arc length. Sorry, you have the change into the arc length. So the change into the arc length, you can change it to the what? We can change it to the differential of the arc length. Differential of the arc length. And since this everything depends on the curve, so we can introduce this notation. Okay, so that's just the motivation. I'm going to make it official and write it down for you. This new integral that we got over here, everything just makes sense. It's like the one that we did for the function of two variables. So as usual, if you partition it as you like, pick this point as you like, and this limit does exist, in that case, we are going to call it integral of f of x y ds over s, and this is going to be called the line integral. Okay, so it's going to be the line integral of the function f along the curve C. That I'm going to make it official and write it down as a new integration that we have. Any question? So this is just a motivation so far. Okay, we want to give you as a definition, but we want to know what's the origin and how we pointed together. Okay, everything makes sense. Okay, everything makes sense, like the one that we did for the function of two variables. We have no difficulty and we know how to arrange it. Of course, it's not going to be easy so far to do it, but you will see the connection right away in a minute. Okay, is this the same as the contour integral? Somehow, yes, it is. Yeah, contouring integral is just the line integral. Yeah, the expression contour integral we use for the complex functions. If you are going to be in the complex analysis, we refer to them as the contour integrals. And you can talk about the contour integral over here too. Okay, all those integration that depends on the path, and we call it contour integral. But contour is the expression that we use for the complex functions. But it's the same thing, yes. Okay, there is going to be, when we do it in those concepts, there's going to be a difference. Okay, in the complex variables, you know that we change this function f of xy as a f of z, then this would be dz. But then dz would have a similar thing over here. Yeah, it's the same thing, but in a concept of the calculus 3, we usually refer to the line. Yeah, it's the same thing. Okay, let's make it official to get these numbers. It would be beautiful, you know, when you do it with the complex variables, because when you do complex variables, you can bring, you know that any complex numbers can be written as a plus bi. Any complex function can be written as a u plus iv. And that u and the v would be a function of two variables, x and the y. So if you have this procedure for a u and the v, then you can extend it to the function of the complex, okay, complex variable function. So that's that general one. They refer to the contour integral. Okay, so let's make it official. That is going to be the case. I used to teach complex variable when I was, in a large university. I was the assistant professor over there, and that was one of my favorite courses. And I have a book, a textbook on the complex functions. Okay, so let's do it. If a function. So we make it official, whatever we did, the definition, if, okay, if f is defined. So far, it's a great notion, okay? It's defined on a smooth curve, on a smooth curve, let's see. Okay, then the line integral. The line integral. Okay, the line integral of f, of the function f along, okay, along the path C, along the curve C, is going to be defined by, okay, is defined or given by, that's the formula, okay, integral. That's it. You can say integral from a to b, or we usually write integral of f of x, y, okay, ds, and we put the c here along the c, okay, along the c, it's going to be equal to the limit. Okay, it's going to be equal to the limit of the sigma, the one that we did. Okay, it's going to be different notation. F of, let's say, xi star, comma, yi star. We already defined this. Makes sense. Delta si, okay, I from 1 to n, when n goes to infinity. Of course, if this limit exists. Okay, so that would be our definition of, and of course, if this f is continuous, we have nothing to worry about. If f is continuous, then everything does exist. F is going to be continuous, then we can change this one into this format. Okay, it's going to be integral from, can say that a to b f of x comma y. This is going to be differential of the, okay, arc length. And this is going to be integral from a to b. Okay, integral from a to b. And then you see this x and the y would be changed into the function. It's going to be x of t, y of t. Okay, and then you know the differential of the arc length. Remember the arc length. I'm going to create it to see it, but I write it down first. This is going to be the norm of the r prime of t. Okay, and the dt. When we switch it, and when you want to find it, this is the way we're going to do it. I can show you why this is going to be the case. So this is going to be computing format of this formula. Just to remind you how we did this one, it's not a big deal, but it's nice to know. Note that. Remember the formula for the arc length. Arc length is what? What's the integral of this of what? Dx dt all squared. Okay, plus dy dt just was a speed. Remember, integral of the speed. So that was the arc length, or in short, this is simply L is equal to the what? It's going to be integral. This is from A to B. It's going to be R prime of T. This is going to be D of T. Okay, in general, or along the C that we're going to have. Okay, so that's the formula for the arc length. But if you want to consider differential of the arc length, okay, so the differential of the arc length means differentiate. So the differential of the arc length is, you know, that the integral would drop, and differential of the arc length would be r prime of, would be a speed. It's just a speed, so this is going to be a ds. Okay, and you know that this is going to be again the same as, this is going to be the same as x prime of t squared, because you have to evaluate it, and y prime of t all squared. Okay, so that's why that integral that I talk about it. So the line integral fxy ds, as we talk about it, we can change it to this format that we're going to have. So it's going to be integral from a to b. The function is going to be evaluated at the curve, x of t, y of t. Okay, and this is going to be the norm of the r prime of t and d of t. Okay, this is going to be the case, but you know that this is going to be simply the equation of a curve, which is going to be r of t. So simply your formula is going to be this one, integral of f of x y ds. The line integral along the curve C is simply integral from a to b f of r of t. Okay, everything would be a scalar value. Okay, f of r of t, and that would be the norm of the r prime of t dt. This is going to be the formula. You know, I put it up there, but I just want to show you what it is. So this is your formula to finding the line integral. So the curve C would be given to you. There are two cases. Equation directly would be given to you. So you have the R of t, but most of the time you get the description of the curve. If you get the description of the curve, you have to find the parametric equation yourself. Okay, and the cases are going to be circle, semicircle, straight line. So you have to get it into you get a parameterization of that equation. So simply you find the norm of r prime of t, you derive the function in it, and then you know we get. It takes a little bit time. Sometimes it's messy, depends on the equation that we have, but it's not bad. It's going to be a straightforward problem to get through it. Okay, any question? So this is your formula from now on for the line integral, and we are going to, of course, the function is a function of two variables. What we are interested is in, you know, talking about vector fields, but we get to that one. So we need this one to be able to get it, and you must know the difference. Interpretations, talk about the, the arc length, traveling bond. But if you want to get more like the area problem, you have to consider this function to be positive. So if f is positive, okay, if f is continuous and positive, you know that this function is a scalar value, real value, so we can talk about the positive or negative. And f of x comma y is going to be non-negative. Then you can interpret this one as, you see, if you want to find the area of a fence, or if you want to find the area of a curtain, if you like. So if you have, if you have a curtain, you say this is going to be a curtain. And if you want to find the area of this curtain, so the situation is just partitioning one that we talk about it. You see, it's like in an ordinary one, you just get rectangles. But over here, those partitions are not going to be just, okay, they're not going to be rectangle, because these lengths are going to be curvilinear. So instead of the distance, the length, so what you do, you use the arc length. So that's the interpretation, if you like, So if it's going to be continuous and negative, then you can consider as this integral, okay, as is the area. We have other consideration from physics, but you have to wait. But this is going to be, when we change it to the vector field, then physics will come in. So of a fence, if you like, or a curtain. So that's, it's a nice interpretation so far, curtain. Okay, so this is the line integral. Okay, any question? Your job, just find it. We give you one of them, okay? This is going to be just straightforward. You don't have anything special about it. As I told you, you have to be patient to put it together, and you're going to use it again and again when we get to even to those vector fields. So be patient, and it's fine. We have nothing to worry about. So I have to give a couple of examples. Those standard one to see, especially if we have the difficulty, not difficulty, just considering this curve and the equation that we have. Otherwise, if you have the R of t integral is easy, it's going to be just a usual integral, and we'll be able to find it. Sometimes a couple of change of variable substitution method, otherwise straightforward. Okay, are you ready? Let's take the example of how we're going to apply it. So make sure you add this one to your collection of your formulas for the line integral of a function of two variables so far. Okay, let's check to see what's going to be the challenges or the way we want to do it. Okay, so let's start with the straightforward. Everything would be nicely given, and then we change it. Are you ready? Evaluating the first one. So we'd like to evaluate this function. Evaluate this integral of a 2 plus. Okay, it's a 2 plus x squared y ds. They use this notation, so there's going to be line integral. Then they have to give us where is the c. Okay, this is going to be the case when c is the upper. Okay, it's going to be upper half of a semicircle, of the unit circle, and unit circle with this equation, x squared plus y squared equal to 1. That's it. Okay, and there you are. Solution, you know the formula. To be able to do it, just repeat the formula. So this is it, the line integral along the c is going to be integral from a to b f of r of t, okay, norm of the r prime of t dt. So the first thing to do, you have to find the r of t. So this is going to be your first job. Where is the function? The equation of a curve. In this case, the curve is a semicircle. Okay, this is it. So you have the unit circle. Okay, from -1 to 1. So you have to get the parametric equation of this. You know the parametric equation of a circle that we are going to use it. So from now on, just use the polar coordinate that give you parameterization of a circle. So you're going to use this quite a lot. So parametric equations, okay, of C. Going to be your X is just unit circle R cosine of the data. Oh, we go with the T, and its unit circle R is 1. So that give a cosine of T. Okay, this is how you behave. You check the circle. And this is going to be R equal to the sine of T. Okay, and R, remember R is equal to 1 is the unit circle. So that gives sine of T. Okay, so your equation is going to be your R of T. Remember your R of T is X of T, XY, X of T, Y of T. So in this case, you have what? You have a cosine of T, and sine of T. But since it's just a semicircle, so your T is going to be between 0 and pi. Okay, so that's the important part of the problem. And now, any question? So find R prime of T and the norm of the R prime of T. So we need R prime of T, which is going to be negative sine of T, and you get a cosine T, and norm of the R prime of T. That's going to be the square of these. I write it down just to remind you. It's a negative sine T squared plus cosine T squared. It's going to be sine squared, cosine squared would be 1. So radical 1 equal to 1. Nice. Nothing to worry about. That's it. You can go to the formula or you can substitute for the F and go, this is depend how do you want to handle this problem. So this is it. It's going to be the function. Remember, this is it. You want to find this integral, which is going to be 2 plus x squared y ds. So we change it. The integral t goes from 0 to pi. 0 to pi. We change this one. I'll just write the formula for you. So it's going to be f of rt. Okay, f of rt, norm of the r prime of t and the dt. Now substitute. So it's going to be equal to the 0 to pi. This is your function, but you have to change it to the t. So you have your x is cosine of t and y is sine of t. Okay, you substitute and you go for it. Okay, I just write it down so to remind you. It's going to be f of cosine of t for the x, sine of t for the y, and the r prime of t is equal to 1 dt. Okay, we usually substitute right away. This is the first one I just explained. Okay, so this is going to be 0 to pi. You substitute, it's going to be 2 plus x squared, so that gives you cosine of t squared. Okay, and the y, sine of y. Sine of y and dt. Okay, any question? So integrate, usual integration. So integral of a 2 would be 2t. Okay, so that's going to be 2t. Then over here, you have the power function. You take this one to be u. Okay, you take this one to be u. You need the u prime. You know that u prime is negative sine. Okay, negative sine. So if we can put the negative here and just apply the u squared. So the derivative would be cosine cube of t over 3. And it's going to be evaluated from 0 to pi. Any question? I just integrated right away respect to the t. That give you 2t. And this is, you have to use the chain rule, okay, or substitution method. So this is u, you need to pair it with u prime. So there is a negative sign that's missing. So that give you negative cosine cube over 3. So just substitute, simplify, you're done. So if you put the pi, that give you 2 pi. Okay, 2 pi minus cosine of 0. Cosine of 0 cubed over 3 is going to be minus. If you put the 0, that give you 0 minus, sorry, that's cosine of pi. Cosine of pi, I put the pi. So that give me 0, and this is going to be cosine of 0 cubed over 3. So the first part is just a 2 pi. Cosine of the pi is a -1. -1 cube would be negative, negative would be positive, so that we have positive 1/3. Okay, and over here, the cosine of 0 is 1. So this is 1, this is a -1. So the cosine of 0 is going to be 1, but it's going to be -1/3, but it's going to be positive 1/3. Positive 1/3. So it's going to be 2 pi. It's going to be 2 pi plus 2/3. Okay, we can use your calculator if you like, but we accept it. So that would be the result of the integral. Any question? So as soon as you substitute, just make sure you don't miss anything. Okay, when you substitute it, it's going to be a straightforward integral. Okay, so the situation they're going to have, just the equation of the line is important. Okay, this is the first one. Question? Now, most of the time when we have, you see, when we go from one point to the other point along the curve, you may have along the curves. So you may have to do several curves, several paths to get through, to get through to the point B that you are interested in. Sometimes you may have just a straight path, a straight lines, but sometimes you may have a curvilinear one. So what we can do is, if you have a collection of curves, and then you have to go through it. So the way you can do it, you can break the integral to different parts. It's like, when you want to find the integral from A to B, if we pick a C, so we can break it into integral from A to C, then C to B. So that's the same thing can happen here, because the situation here is just ordinary function. So we give you a remark, and most of the time these are the domains or the curves that you're going to have for integrations. Okay, so we give a remark. If you have to go through a collection of curves to get to your destination, so you have to break your integral accordingly. So if C, okay, if C is going to be a kind of a piecewise, means break it into parts, okay, is going to be a piecewise. Okay, piecewise, a smooth curve, we call it piecewise, a smooth collection. Okay, piecewise, a smooth curve. Then, of course, C is going to be the union of some curves. C is the union. There's going to be union of subcurves. Okay, subcurves. And these curves, let's call them C1. Okay, C2 up to something like Cn. Then the situation is going to be, this is it, this is the way we denote it. So we have a union of these curves. Okay, the unions. We get to the Cn. So the line integral on C would be the sum of the line integrals on each of these subcurves, if you like. Okay, so this is going to be the case. So therefore, again, it's exactly the same for the complex functions or the contour integrals. So that's going to be f of x comma y ds on the C. You have to break it. So it's going to be integral of the first one. Okay, the integral on the C1, on the C2, you just continue. Okay. So you continue to get to the last part. ds and the Cn. Okay, any question? It's, is the usual practice. Then we put them together. Look at this. Of course, these must be exist to be able to get to the last part. So this is mostly your job. Your paths are going to be mostly a connection of one, or it's going to be two, or so we are going to check it, and eventually these are going to be so nicely simplified. Okay, it's like, but you have to know it, because some cases we can't do it, but most of them are going to be clarified as by using two great theorems, especially called it Green's theorem, and of course fundamental of calculus. Okay, so let's get one practice on this one. Okay, because this is the one that you have to do. So you have a couple of nice one in your practice quiz number 4. I'm going to update it this afternoon so you can have them. Okay, so, and of course they are part of your final review. The 5 last problem of the review on the final review are of this section. Okay, let's take the integral. So you want to evaluate this integral. Okay, evaluate the following integral. Integral is easy, 2x ds. Okay, over a curve C, along the C. So where is the C? Where or when? C. What is C? C consists of, C is going to be consist of the, okay, of the arc. Okay, a curve of the arc C1 of the parabola. This means part of the parabola. Parabola with the equation y equal to the x squared. Okay, from this point, from 0 to 1 1. So this means you travel from 0 0 to 1 1 along this curve, y equal to the x squared. So this is going to be the equation of your curve. And of course, you have to parameterize it. Okay, then you continue with the other part. Okay, so this is going to be the case, but you follow by the following. Followed by the vertical line, by the vertical. Okay, followed by the vertical line segment. Okay, go along the segment line, a straight line. Okay, line segment C2. Then you go from, you see, you end up with the 1 1. Now you start with the 1 1 from 1 1. Then you go to this point, 1 2. You see, that's going to be the kind of problem that we're going to have. So you have to do it twice if you like, because you have the C1 and the C2. So get a graph of this situation that you have. You identify. You have to call one of them C. You already got one of them C1, C2. So it's a combination of 2, and your integral is going to be. You have to break it. Okay, so this is going to be the solution. So basically, officially, you have the C is equal to the C1 union C2. So the integral that you have to find is 2x ds, okay, on your C. So you have to break it in 2 parts, on the C1 and the C2. Okay, so I'm going to take each one separately. Just find it and just come back. The situation I'm going to have. Okay, let's look at this, the path that we have. So your path is going to be this one. You see, you start with the point 0 0. You go to the 1 1. This is 0. This is going to be 0 0. Okay, this is going to be 0 0. Then this is going to be our 1 1, and this is going to be 1 1. Okay, it's going to be 1 1. So you go along this the curve. Okay, this is what you do so far. Okay, it's going to be just C1. Okay, so these paths, okay, you get these paths. So the path, this blue one is going to be the C1. C1. It's easy to get the parametric equation. You see, you have y equal to x squared. So x is free. We can call x t. Y would be t squared. So your r of t is going to be t and, okay, so it's going to be t and t squared. You can save with the x if you like. You have to go with you have to change the coordinate. Okay, then we are going to explain it. So that's going to be the situation. So we get to this point. So what do you do next? So what you do next is you go from 1, 1, which is this point, you go to the 1, 2. Where is the 1, 2? This is 1. Okay, this is going to be 1, and this is going to be 2. So this is a 1, 2. But you go along a vertical line. So this is going to be 2, 2. You go vertical line, and you get to this point. Okay, and this point is going to be what? This is going to be 2, 2. Sorry, this is 1, 2. 1, 2. So this black one is going to be your C2. Okay, it's going to be C2, which is going to be easy to get the parametric equation of this one, because this is a vertical line. Since it's a vertical line, you know that the equation of this line is simply what? Is x equal to 1. So x is fixed and the y is free. When it's a free, we call it t. And then we get those equations. Okay, so basically, I'm going to explain it, but if you like to get this equation so far, your C1 is going to be, this is going to be the C1. If you want to get the C1, it's y equal to the x squared. So x is free, you call the x to be t. So this is going to be x equal to the t. Okay, x equal to the t, and the y would be t squared. And you have to give us a range for the t. Your range must be so that if you start with the initial point, you must get 0, 0, and then get a 1, 1. So in this case, your t is going to be between 0 and 1. And you check it, when t is equal to the 0, that gives you 0, 0. When you put t equal to 1, that gives you 1, 1. Okay, so, you know, if it's not, you just to modify it to get, you know, to get the different one. Okay, so it's going to be C1, and the C2 here, you can get the C2 later or just now. What is the C2? C2, you go along a vertical line. So this vertical line is going to be a fixed line. Okay, the fixed line x equal to 1. So your x is equal to 1. That's your vertical line, but your y is free. You can go up, 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 up. So y is free, so your y is equal to t. That's going to be the case that you have. Now what's going to be the range for your t? Remember, you want to go from 1, 1 to 1, 2. So x is equal to 1. So this means your t is going to be, you see, initially at the beginning, t must be equal to 1. So that gives you 1, 1. And you end up with the 2 for the y. So it's going to be less than or equal to 2. So these are going to be parametric equation of these two curves that you need to know. Any question? So when the equation is given to y equal to the x squared, you're parameterizing yourself. Because x is free, it's a parabola. So you get x equal to t, but y would be t squared. Okay, and depends on the points, you can identify the t. This is going to be 1. And the other one was a vertical line. The vertical line, the equation of the vertical line is x equal to 1. But you know that when it's a vertical line, your y is free. You can go up, 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 down, 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 as much as you like. So you call it y equal to t, and then you restrict the t into this section because you are interested just as 1, 1, and 1, 2. Or initial value should correspond to the initial point. So if you put t equal to 1, that gives 1, 1. And you put t equal to 2, that gives 1, 2. So this means everything is set up nicely, and we are able to find the integral. Okay, any question? So let's do it. We have 2 to take care of. So this is it. So taking care of the first one. Okay, taking care of the first one. which is a 2x ds, okay, c1. This is going to be your integral, and as we talk about it, your t is going to be between 0, 1, and this is going to be the formula f of rt norm of the r prime of t and the dt for the first part. Okay, remember this is it, your r of t now is going to be, as we talk about it, x and the y. So your x was t and the y was t squared. Okay, this is it. So you differentiate it, r prime of t. R prime of t would be 1, 2t. So you have to get the norm of this. Okay, the norm of the r prime of t is going to be the square root of, that would be 1 squared plus, it's going to be 1 squared plus 2t squared. So that gives you a square root of 1 plus 4t squared. So this would be your r prime of t. So go back, substitute here, and f of rt, you see this is going to be the case. So what's going to be the case? The case of 2x ds over c. I bring this one down. So it's going to be 0 to 1. You have to evaluate the function f, which is a 2x at this. So your x is t. So that would be 2t. You substitute, you see f of rt. This is it. X is t. Y is t squared. You have 2x, so it's going to be 2t. Then a square root of, nicely, you have the 1 plus 4t squared. Okay, then the tt. Any question? So if you just rewrite it, you'll find out everything is almost there to integrate it. Okay, so for the substitution method, you take this one to be u. Okay, if you take this one to be u, then u prime would be 8t. So if you want to do the shortcut, you need an 8 here. So what I do, I divide by 4 and multiply by 4 to create that one. Okay, so I rewrite it as a quarter, then 8. Okay, 8t. So that gives me 1 plus 4t squared to the 1/2 dt. Integral from 0 to 1. Okay, so there you are. And so I have the kind of, this is going to be the u, and I have the du if you like. So it's kind of u to the 1/2. Okay, so I integrating u to the 1/2. Du, which is going to be, that u to the 3/2 over the 3. So I can continue. This is going to be a quarter. Okay, this is going to be the quarter, and the u, which is 1 plus 4t squared to the 3/2 over the 3/2, and the integral from 0 to 1. Use the reciprocal of the 3/2, then substitute. So it's going to be a quarter. Reciprocal would be 2/3, and the 1 plus 4t squared to the 3/2, going from 0 to 1. Okay, these two would cancel out. So that give you 1/6. Okay, that would be 1/6 and 1 plus 4t squared to the 3/2, going from 0 to 1. It's not going to be a nice number, but we can use your calculator, just write it down as is. So if you put the 1, that give you 1/6, 1 plus 4 to the 3/2, minus, if you put the 0, so that give only 1/6. Okay, so it's going to be a kind of 1/6. Yes, it's going to be 1/6 times the 1 to the 3. Yeah, so it's equal to the 1/6. 1 plus 4 would be 5. So it's going to be 5 to the 3/2 minus 1/6. Again, use calculator, or if you want, it's going to be 1/6. 5 to the 3/2 would be 5 radical 5. So it's going to be 5 radical 5 minus 1. Again, you can use your calculator to get the decimal number for this one. Okay, so that's the first part. So that's so far you're integrating when you're going from the 0, 0 to 1, 1 along that, along that parabola that we did have. Now we have to take it from that, do it for the straight line or that vertical line. Any question? So this is the most you do. We get those integration by parts. Okay, so we get to the second part. So then we add them together. So the second part is you have to find the integral of a 2x ds, but use C2. Okay, remember the situation that we have is a 1 to 2. So it's going to be the case. I just remind you the C2. The C2 is x equal to 1, y is equal to t, and the t is between 1 and 2. That's the situation that we have. Okay, so we get you get r of t. R of t for your curve is going to be x and y, which is going to be 1 and t. Then you need r prime of t. So the r prime of t would be 0 and 1. So the norm of the r prime of t would be just 1. So you don't need it. So the norm of the r prime of t is going to be the square root of 0 plus 1, which is the radical 1, which is equal to 1. So it's not going to be causing any difficulty. So just go back and get the function done. It's just a 2x and x is 1. So the integral is straightforward. Okay, so we substitute. This is it. Integral on C2 dx 2x ds is going to be equal to integral from 1 to 2. It's going to be 1 to 2. The function 2x at 2 times 1. Norm of the r prime of t, which is 1, and the dt. Okay, so we're just integrating 1 to 2 dt, which is going to be 2t from 1 to 2. So it's going to be 4 minus 2, which is 2. 4 minus 2, which is equal to 2. So the integral on the second part, 2x ds over c2 is simply equal to 2. Okay, for the first part, we get this one. For the second part, we get 2. Just add them together. That gives you the final answer. Okay, so I write down here the conclusion is going to be the given integral was 2x ds over c is going to be just, again, you can use your calculator. Otherwise, this is the way we write it down, plus 2. So that gives you the final answer. Okay, again, as you can see, it's not difficult, but you got to be careful when you put these numbers, together to be, to be able to do it. Okay, so this is what we did so far. But of course, the function was a function of 2 variables. If you want to do it in 3 variables, everything is going to be the same. Again, this is a scalar valued function. Okay, so let's have a break. We come back. We have to give you one example on the scalar valued with the 3 variables. Okay, f of x, y, z. And then when we take care of that one, then we can go and extend it to the vector fields. Okay, these are, remember, all of them, the range of these functions are numbers. So we are aiming on the type that the range of this function is going to be a vector. Okay, and we modify it nicely, and then we be done. Okay, it's 12 o'clock. It's a between 10 and 15 minutes break. Then we come back and we do that extension, and then we extend it to the vector field, which is our target. Okay, see you then. Okay. So what we did, we just introduced the line integral for a function of 2 variables, okay? A real valued function. So we can extend it to the 3 variables, okay? It doesn't matter. Just, this R of t is going to be X, Y, Z. So let's make it official. Okay, that the situation will be the same. So that would be a line integral. Okay, that's it, the line integrals. Line integrals in space, in 3 space, if you like, or a space. Space. So everything is stay the same, just the function, and the function is going to be a function of 3 variables, and your curve is going to be a curve in 3-dimensional. So suppose, okay, suppose C is going to be a smooth curve. Okay, a smooth curve in a space with with the equation. Okay, with the equation R of t equal to X of t, comma Y of t, comma Z of t. And this is going to be your t is going to be between A and B. Okay, if this is going to be the case, then we can define the line integral for the function of 3 variables, f of x, y, z. Again, differential of the arc length over c. So it's going to be the same thing, integral from a to b. Okay, f of r of t, then norm of the r prime of t, then d of t. Okay, so far we are going to be safe, everything is going to be consistent, if you like, because again, you have a real valued function. Okay, the function is function of 3 variables, and the range is a number. Okay, any questions? So let's get one example on this one, and then we prepare it for the big one. So what's going to be the example? Example is going to be the following: evaluate this integral of the y sine of z ds, okay, over c. That's your function, and this is going to be evaluated where c is going to be the circular helix. Remember helix? Circular helix given by this equation. Okay, given by the equation and this is going to be your equation. X is equal to, that in 2 dimensions it's going to be just a circle. So it's going to be cosine t, y equal to the sine t, and the z is free. Z is equal to t. That's the equation of the helix. And they wanted when t is between 0 and 2 pi. Okay, so situation is clear. So quickly, you have the equation of your curve. R of t cosine t sine t. We can find the r prime and the norm, and then go back and find the integral. The integration of the helix is usually easy integral to handle. Okay, are you ready? So this is going to be our solution. Let's get the equation of the curve, which is given. So we have R of t, which is going to be equal to the cosine of t, sine of t, and t, and your t is going to be between 0 and 2 pi. Okay, so differentiate it. R prime of t is going to be equal to cosine would be negative sine t. Sine would be cosine t, and the derivative of t is 1. So that's going to be R prime. Get the norm. So the norm of the R prime of t is going to be equal to just the square of those components. So we get negative sine t squared plus cosine t squared. And we get a 1 squared, which is 1. Sine cosine, that give you 1. Okay, secant sine squared, cosine squared, that give you 1. So we get a 1 plus 1. So we get the radical 2. So nothing to worry about. So we got the R prime of t. Then evaluate the function at R of t. So your x is cosine of t, sine of t, and the t. Okay, and the function is y, sine of z. So we have substitute for y, which is the sine of the t. And then sine of the z would be changed to the sine of the t. So it would be easy integral to handle. Okay, so there you are. So the given integral is y sine of z ds is equal to, so integral would be changed into the t format, and we have a 0 to 2 pi, 0 to 2 pi. Evaluation of the function at R of t, so the y as we talk about it is sine of t. Okay, so y would be sine of t. And then you have a sine of z, z is t, so that gives a sine of t again. Okay, and there you are, R prime of t. R prime of t is the radical 2, norm of the R prime of t is radical 2. Then we get the dt here. So that gives a sine a square, and the radical 2, you can bring, pull out the radical 2. So that gives a radical 2 integral from 0 to 2 pi. Okay, 0 to 2 pi sine a square of t dt. You have to integrate sine square, you know that. Integrating sine square and cosine square, you have to use double angle. So double angle formula is going to be radical 2, 0 to 2 pi. Okay, 0 to 2 pi sine square, you know that the sine square is 1 minus cosine of the double angle, 1 minus cosine of the double angle, which is 2t. Okay, 2t over 2 dt, double angle formula. Okay, you can break it and then integrate it, or you can pull out the 1/2. So the 1/2 out, that give a radical 2 over 2. Okay, integrating from 0 to 2 pi. Okay, 0 to 2 pi is going to be 1 minus cosine of the 2t dt. Okay, that's going to be the case. So this is a radical 2 over 2. So we integrated, the integral of 1 is t. Integral of a cosine is going to be a sine. So it's going to be minus. That's the sine of 2t. Then you have to divide it by 2 for the u prime. Okay, and then evaluate it from 0 to 2 pi. Okay, integral of 1 is equal to t. Integral of a cosine is sine, sine of the 2t. But the u prime would be 2, so you have to divide by 2 to just make sure to get it right. Then you just substitute it, get the result. If you put the 0, sine 0, everything would be 0. So you get only when you put t equal to 2 pi, that give you 2 pi. The sine of the 4 pi is also equal to the 0. So we won't get anything regarding those. Okay, so this is it. This is going to be radical 2 over 2, just the 2 pi minus the sine of the 4 pi. Okay, 4 pi over 2. So the sine of the 4 pi would be 0. So that gives you radical 2 over 2. okay, times it by the 2 pi, which is going to be pi radical 2. So that give you the final answer. Okay, so the procedure is going to be the same. So everything makes sense to be able to do it. Any question? Now, when we get to the function of 3 variables, sometimes these notations can be, you can extend these, okay, the type that we have over here, these functions, okay. You can write on it x, y, z, and then you don't have to stay with it. We call it the differential form of this. You don't have to stay with these dx, dt, everything would be changed into the kind of new form of the integral. So I give you one of them, and all these integrals eventually would be of this form. You see, look at this one. We can show you in general that this integral would be changed in this form, but this is the form that at the end you are going to do. Okay, when we get to the Stokes theorem, we get this type of format. Look at this. We want to evaluate this integral. Look at the integral. It's a line integral, but they give you differential form. You see, y dx plus z dy plus x dz. You see, these are going to be the type that you have for this integral. In general, this is, when you get to the function of the variables and the vector field, the vector field, the functions are p, q, or m and p. So this type of form are going to be useful over there. So it's a line integral. It's a line integral when you substitute for the function. You remember the x, y, z would be x of t, y of t, z of t. Then the dx is just x prime of t, or is going to be x prime of t dt. So you have to substitute directly to get these numbers. Okay, so it's the same thing. So I want to evaluate this where what is going to be c. Where c consists of, there is another method to evaluate these integrals in future. So that's why I wanted to get the experience. So you want to find this integral when c consists of, okay, consists of the line, consists of the line segment, okay, line segment C1 from this point 2, 0, 0 to 3, 4, 5. 2 different points. So C1 is you start from this point to go to the others, okay, followed by the vertical line, by the vertical line segment, vertical line segment C2. Now the C2 would be from the point, of course, 3, 4, 5. 3, 4, 5 to the point like 3, 4, 0. So the paths are going to be just straight line, if you like, a straight straight path. You're going from these points, okay, to the 3, 4, 5, and then followed by this vertical line. You see, because the 3 and the 4 are all constant. So just changing the z, if you like, to the 0 and 5. So what you're going to do, you have to break this integral 2 parts. Okay, the part for the C1 and the C2. So you have to find the parametric equation of each part first. Okay, then when you substitute as is. So you know the x, y, z are going to be the one that's coming from the equation of the curve. And your substitute is a direct, finding the direct integral over here because it's already given to you. All those, the formulas that we did, we can change it into this format. Okay, so we have to break it in two parts. Solution. Again, this problem can be done with different methods in future. So we start with the C1. C1, you have to find the parametric equation of the R of t. What is this curve? This curve is going to be a line segment from the 2.00 to 345. Okay, you know that how we're going to find the equation of this parametric equation of the line. Remember, we need a kind of a point and the slope type. Just remind you the equation that we did before. You see your R of t is going to be R of, let's say we call it T0, remember? It's going to be a point, T0. Then we have a kind of the slope, then the direction of the vector. So this is something like, the way we did it is going to be T times, okay? It's going to be T times just the directional vector that we're going to have. Okay, so this is going to be kind of R prime of T0. Or, so this is the type that we did. Okay, so what we are going to do is, this is it. So this is going to be kind of the slope that we're going to have. So since 2 points are given to this, the way we're going to find it, R of t is equal to, let's start with the initial point. So the initial point would be 2, 0, 0. So that's going to be the initial point, okay, plus t times, in the case of the line with the given 2 points, if you like, remember, the directional vector was what? The directional vector was, so this is going to be the vector. Remember the difference between, because you have to find the component form of the vector. Okay, the vector, I can call this one something like V of T0. Okay, to get that vector for you. And remember the difference, A minus B, so it's going to be 3 minus 2. This would be 4 minus 0. And this would be 5 minus 0. It's the way we find the equation, parametric equation of a line passing through 2 points. Okay, so if you simplify it, so what's going to be the case? It's going to be equal to the 200 plus t. You simplify this. There are other ways to do it. I just want to show you this method because this is a general method. It can be used in a general form. So it's going to be 1, 4, 1, 4, 5. Okay, and just keep going. If it's going to be equal to what? In a vector form, it's going to be 2 plus t times 1, 2 plus t. Okay, and this is going to be what? This is going to be 0 minus 4t. Okay, so that gives you 0 plus 4t. That's going to be 4t. Okay, and the last part was 5t. So that gives you the equation of the equation of it. Okay, you know that x minus x0 over a equal to that parametric format that we have. Y minus y0 over b, remember, this is the same thing. So this is going to be the parametric equation. So that gives you a parametric equation of a C1. Of course, you have to pick the t so that you get the initial point at the beginning. And at the end, the beginning is 200. So we pick the t to be equal to the 0, because that will give us a 200. And to get to the last part, we need 3. So if you pick t to be between 0 and 1, you are fine. If t is equal to 1, that gives you 3, 4, 5. Any question? So that's, kind of the one that we're going to use quite a lot. So it's just a parametric equation of those line that we have. So that's going to be the C1. Let's stay with the C1, continue. So now what we need is, since they have to give you x, y, z, so you realize that your x is equal to 2 plus t. Your y is equal to the 4t. And your z is equal to the 5t. So that's going to be your x, y, z. Now you find the differential of the x, differential of the y, and differential of the z. So your differential of the x would be the derivative, which is 1 times the dt. The differential of the y would be the derivative 4 times the dt. And differential of the z would be 5 dt. You see? Go back, substitute. You see? Go back, and you are going to use these two to substitute into your integral. And then you integrate it. At the end, integral would be just integral of the respect to the t. Okay, so let's go back. What do you have? We have the y dx plus z dy plus x dz. You want to find it on C1. So it's going to be integral respect to the t. T is between 0, 1, 0, 1. Y, this is it. Y is 4t. 4t times dx. dx is dt. So that's the first part. Plus z. Z is 5t. Z is going to be 5t. Okay, so that gives you 5t times the dy. dy is 4 dt plus x. X is 2 plus t. 2 plus t times the dz. dz is going to be 5 dt. Okay, I just directly substitute to get these numbers. Okay, multiply it, simplify it. This is it. You can pull out the dt as your differential and then take care of the others. So it's going to be 0, 1. So I have the 4t here. Then I got the 5 times 4, 20. 20t. Okay, and over here, 5 times 2 would be 10, and the 5t. Then the dt. Okay, so I pull out the dt and I simplify the rest. Okay, so it's going to be 25 and 4 would be 29. So this is going to be the integral from 0 to 1. Okay, 0 to 1, and this is going to be 29t plus 10. Okay, plus 10 and the dt. Okay, now we integrate with respect to the t, which is going to be easy integral to apply. So 29 t squared over t plus 10t to be evaluated from 0 to 1. Now we replace the t by 1, so that gives it 29.5 plus 10. Okay, the common denominator would be 2, so that gives you 29 plus 20, which is 49 over 2. So that would be the integral of the, integral of the first part. Any question? So that's respect to the C1. You have to repeat it again. This time for the C2, it's very similar because the C2 is just a vertical line. That's easier. You can check that one quickly and do the same procedure to get it. Okay, any question? So I just want you to see it right at the beginning because this is the one that you're going to do in future. We have a kind of 2 different methods to integrate, and then sometimes we want to confirm it, that both of them are the same, especially when we get to the last part of the course. There is a great theorems. We call it the Stokes theorem. Then you do this confirmation for us. Okay, are you ready? Going to the C2. So remind you, what's the C2? C2 is going to be a line. Okay, just connecting the point 3, 4, 5, a vertical line to the 3, 4, and 0. You can write this equation right away if you like, or just do the same thing that we did. So R of t is a straight line. And the starting point is going to be 3, 4, 5 plus t times the directional vector. The difference, 3 minus 3, 3 minus 3, 4 minus 4, 0 minus 5. Okay, so R of t is going to be equal to, it's going to be 3, 4, 5, and plus t times 0, 0, and then negative 5. So combine them together. So R of t is going to be equal to 3 plus, and that's it, 3 plus 0. You get nothing over there, okay? And the 4 plus 0. And we get the 5 minus 5t. Minus 5t. So that gives you your R of t. So it's going to be the equation of the curve. Any question? Okay, again, since the equation is given to in x, y, z, so identify the x, y, t is going to be your x. So your x is 3, your y is equal to 4, and your z is equal to the 5 minus 5t. Okay, differentials, d of x is 0, d of y is 0. You have only d of z. It's going to be negative 5, but it's going to be negative 5 dt. Go to the function, okay, and substitute. So the integral on C2, this is the function, or the integral, okay, the function expression is y dx, z dy, okay, plus x dz. You want to do it on the curve C2. So for the T2, oh, I forgot to give you the T here. Okay, the T. Initial value is 340. This is it, 34. If you replace the T by 0, so that gives it 345. Okay, if you put the 1, you get the terminal point. If you put the 1, 3, 4, 5 minus 5, which is 0. Okay, so integrating from 0 to 1 for the T. Any question? So let's do it. 0 to 1. Function. You see, this is going to just 4 times 0 because of the dx plus z 5 minus 5 t dy is 0. Okay, then we get the x is equal to 3 times the dz. dz is negative 5 dt. Okay, so these are going to be out. So you're just integrating 3 times 5, 15. So integrating 0 to 1 minus 15. Okay, minus 15 dt. Okay, easy to integrate. That gives you negative 15t going from 0 to 1. If we replace t by 1, that gives you negative 15, and the rest are going to be 0. So it's going to be negative 15 minus 0, which is negative, okay, negative 15. That's it. So in the second part, we get negative 15. In the first part, we get 49 over 2. So the final answer, okay, the y dx plus z dy plus x dz over c is going to be, the first part, 49 over 2. Remember, this is the first part that you got here, 49 over 2. So it's going to be 49 over 2 minus 15, the second part. The common denominator would be 2, so that gives you 49 minus 30, which is going to be 19.5. 9.5, which is going to be 9.5. That's it. So the final answer is 9.5. Okay, so it's a nice one, but this is just to introduce you to this type of format for the integrations. They are very popular. Even we see we are going to use it in application problems, even use it in geometry to get this format. But we are going to take care of it in a minute. Not today, of course, but later on. And if you do again those sort of integration on the complex functions, these are the ones that you're going to see. Okay, any question? So we are building up something, okay, something for these functions or the extension of the integral, line integrals. Now we are ready to get to the big one, really, the one we are interested in. Those are all nice, the one that you did. But you did all the preliminaries, the machine that we need. We need it for the next part. So remember the function that we're working on? These functions are scalar valued. Okay, the range are just numbers, but we are going to be interested in vector fields. So how are we going to do line integrals in vector fields? Okay, so as I talk about it, if you are going to be in the complex case, you stay with this, and then you go on and we take care of different integrals with this method, are going to simplify it. But in our job or our plan, we go to the vector fields, okay? So far you get one or two questions of these ideas, and you're going to do it for all the coming problems. Now, the interesting one is how we're going to extend this one into the vector field, okay? Again, I want to do it just step by step to get the motivation and to learn how you design something. And then at the end of the day, the integral are going to be the same thing that we did so far, nothing new. But you have to set it up carefully. Okay, there you are. That was our target about line integrals of the vector fields. We are still in that section 2.15.2. Line integrals of vector field. The interesting part is start from here through the end of the course, okay? So we want to know how to use it in physics. Remember the vector fields that we're talking about it? Electrical force, okay, gravitational, and the velocity. All of them are going to be using these type of ideas. Now, let's see how I'm going to modify this formula so that you'll be able to use it for the vector fields. So remind you what is the vector fields, okay? Remember, it's a function of three variables in general and in R3. So the domain is in R3 and the range is a vector in R3 again, okay? So let's introduce the function again with the notation that we're going to use for these sections. Suppose C again is the curve. You see the curve is going to be the same thing. C is a smooth curve. Okay, this is going to be a smooth curve. This time in R3, three-dimensional. Now the function is a vector field. You know the vector field in general is going to be denoted by what? F of X, Y, Z equal to three function. Okay. So the expression that they use from now on is this one, PQR. It doesn't matter, but I just stay with the notation that you have in your book so that if you see the problems, okay, so it's not a big deal. You can change it if you like, but this is more popular. PI plus QJ plus RK. You know that this is P is a function, P of X, Y, Z, Q of X, Y, Z, and R of X, Y, Z. Okay, so this is going to be vector field, is continuous. To modify it, we are going to consider this one to be a force. Okay, is a continuous, okay, a continuous force field. Okay, force field in R3. Okay, to get the motivation. You see, if I have this one over here, and if I have, I have the force, if I push it, this is it. If I push it, it's going to be displacement. And what I have done is I have done a work in order to push this one, a little bit forward. So this is going to be our idea. We are going to use the idea of this, the force that's going to be, can be used or can be imposed by this function. So what is going to be definition of the work? So the question is going to be this one. The question is going to be find the work. Let's say W. The work W by the force. By that force. By force F in moving that object. Moving a particle. Moving a particle along along a smooth curve or the smooth curve. A smooth curve C. You see, we are going to attack this problem from this angle, this point of view, a physical point of view, if you like. So let's remind you how we're going to define the force. You know that if you have a constant force, just what is going to be the work? The work is the product of a force times displacement. So just remind you that that's it. Note that what is the work? Note that the work, the work done by a constant force, F, constant force F in moving this particle, moving a particle, moving a particle from a point A, to another point, Let's say B is simply path, in a space, if you like, in a space, it's going to be just a product. It's going to be the work. You got the force. Of course, it's going to be a dot product. Dot product by the displacement vector. You know that the work is a number. Work is a number, but F is a vector. Displacement is going to be a vector. So when you want to multiply to get the number, you have to multiply using the dot product to get this one. This is going to be the case where your D is going to be what? D is going to be a vector from the point A to the point B along that curve that you have. So is the displacement. This is going to be displacement vector that we're going to have. So that's the definition of the work. So I'm going to extend it to the idea that we have. So a situation that we are going to do the same thing as we did for the eventually line integral. And you have to get a modification because of these vectors involved that we're going to have. You see, so this is going to be a situation. So suppose this is a three-dimensional that we have. You see, it's going to be the X, Y, and this is going to be kind of a Z. So the situation that we have to find the work along this curve C again, as usual. You see, that's going to be the curve C that we talk about it. So again, what we did for the other procedure, we can do the same thing over here. If you want to do the work, so we can partition it the curve. This is going to be the partitioning one, for example, that we did have. So it's going to be the P1, the P2, etc. So these are a situation that we have. So the case that we are going to have is if you pick a number like, if you're going to be the same, suppose this is going to be kind of a pi here, a point is going to be the point pi. So, and imposing the force here, you see it's going to be the one. So there is a force. Okay, there is a force that we're going to impose. So this is going to be the force F, and this is the point pi. Okay, that we have to consider. Now, the situation for the three-dimensional, for those displacement that we're going to have is that if you pick, okay, if you're going to be pi and you want to go to the next one, you have to move. What's going to be the direction that you're going to have in order to move? The direction that we're going to get, as usual, we are going to get it in a direction of a, okay, we get this one into the direction of a, you know that the direction for these are going to be the tangent line one. So you have a, you get to the pi or the pi minus 1 and you want to move on. If you want to move on, okay, if you want to move on, you need a direction. So your direction is going to be direction of the, okay, a direction of the tangent line, unit tangent line, which is going to be the t over here. So what we can do, this is going to be the direction. You want to find the displacement that you're going to have. So the displacement, you know that the displacement going from one point to the other point is going to be just the, that's going to be the arc length. You get the arc length over here. But since you want to not only get the quantity, but also you have the direction, okay, because this is displacement. So what we are going to do, instead of the delta SI that we used before, that would be a scalar. So what we do is, since it's in the direction of this vector, so we're just using the vector to be delta S times T, if you like. So T is going to be a vector. It's a unit vector. So when you take the norm, that would disappear. That gives you the arc length again. So the situation they're going to have is the following, that if you want to pick this one at a specific point, you see if I pick the specific point, which is going to be PIS, I want to justify it, okay? If this is going to be a specific point that we are going to call it, as we did it before, XI star, YI star, and this is going to be ZI star, okay? And if you want to find, that to find the work, we find the work in different partitions. So the partition that we're going to have the work of moving, okay, the force would move the particle from the pi minus 1 to the pi is going to be this one. The force is going to be the force at a point, this point, xi star, yi star, zi star, but dot, usually multiplied by the arc length, but it's going to be dot arc length, just to make it a vector, multiply by the delta SI, let's say T star or TI star, it doesn't matter. Okay, T star. Okay, because your force would be in the direction of a tangent line, unit tangent line on this curve. So the displacement would have the same direction of the TI star, and the length of that displacement is going to be the arc length. So the vector that you are going to create is going to be this one. If you find the length of this vector, the norm of the TI star is equal to 1. So that gives you the arc length. So you haven't done anything wrong. Okay, this is a number. You can put it out. So this is going to be equal to, so the WI, if you like, one of each of those work for each partitions. It's going to be something like we get the F, and this is going to be XI star, YI star, ZI star. This is going to be force imposing at that point. Then it's going to be dot TI star. These are all vectors or TI. That makes sense. But then you multiply by a scalar. That scalar is going to be delta SI. You see the difference? The way we are going to construct it is this. The way we did it before, you didn't have this one because you're working with the scalar function. But if you want to stay with the definition of the force, so you need a displacement. Displacement, you need a direction and the quantity. So now this makes sense. So get the limits, okay, put them together. You see the work? The work in question is going to be the limit of sigma of the work on each partition. Okay, I equal to 1, n goes to infinity. N goes to infinity if you have infinity many of these partitions. So your delta SI would be small. So if you put it in this form, this is going to be the limit of the one that we create, the product of the force times the, so it's going to be the product of the force. I just repeat that one, xi star, yi star, zi star times ti star, directional, okay, unit tangent vector at any point. And this is delta SI when I go from 1 to n and n goes to infinity. Now, in the language of integral, this would be what? This would be equal to, it's going to be integral along the curve K, C. The function is question is going to be f function. You see, it's going to be, this is it. It's going to be f function, f of x, y, z. But dot what? That the unit tangent vector, which is going to be a factor at, x, y, z. Then differential of the arc length. Differential of the arc length, which is going to be ds. Okay, these are going to be evaluated at r of t as we did it before. Okay, and then you know the rest that we're going to have. Okay, if I do it in one more step, I go to the next page. Any question? So we're just building up this definition, okay, informally to get the notion of that line integral that you have for the vector field. So I'm going to do a little bit of algebra to simplify this one. My little bit of algebra is going to be f dot t ds. Remember the ds? The ds was norm of the r prime of t. So let's go one more step, and then you will see a very nice formula. Okay, so this is what we have so far. We get the integral. Okay, so it's going to be along the C. So we have a function force dot the tangent, unit tangent vector dot t. Okay, this is going to be the one. Then you have a differential of the arc length. You know the differential of the arc length would be norm of the r prime of t. Okay, d of t. That is going to be the case. But do you remember the tangent line, unit tangent vector? So note that, what is the unit tangent vector? Remember the unit tangent vector is going to be t is equal to, it's a tangent vector which has been normalized. Remember, normalizing it. That's it. We're normalizing. So move it up here. So the W is going to be CF dot T is going to be R prime of T. Okay, over a norm of the R prime of T. Now this is going to be times it by norm of R prime of T, D of T. Okay, remember this is a smooth curve and these are numbers. Scalars is non-zero because of the definition. So this means we can simplify it. If you simplify it, you arrive at the formula, which is very similar to what we expect, but we have to prove it, and we did it. So this is going to be integral. Okay, so I change it to the t, everything. So this is going to be simply the integral from a to b, f dot, okay, this is going to be what? It's going to be f dot r prime of t. Okay, f dot r prime of t, then d of t. Okay, this is it. It's going to be then d of t, d of t. So I go one more step. It's going to be a to b. It's going to be f dot r prime of t d of t. You know that r prime of t d of t is going to be what? It's going to be differential of the r. It's going to be differential of the r dr, and nice. We get the work. It's going to be a to b. Okay, f dot dr. Very famous formula. That's it. This is going to be worked down. I'm going to make it official, write it down for you. But I just want to find it so that you get the idea of how we arrive at this. Okay, some people, they say, oh, it's very similar to the one that we did, so what we are bothering about? No, it's not, because this is f dot dr. When it's a scalar function, you see a scalar function, you just to give a number, remember f of x by z, so you just multiply by the norm of r prime. But in this case, we just change it accordingly, and this makes sense, okay, to get the integral and get through this one. Okay, any question? I'm going to make it official. Whatever I did is called the work. You have to know it by the name of the work, because you are going to be given problem. We give you the force and we ask you to find the work. We are not going to ask you to find the integral. So you must know it yourself, that what we are talking about. Okay, so let's do whatever, put it official. Whatever we did, the conclusion is this definition. It makes sense, okay, to spend a little bit of time to understand it. Okay, it's what's going on. There you are. This is the definition of the line integral for the vector field. So if you have a nice vector field, if f is continuous, you need continuity to guarantee that this integral does exist. If f is a continuous, okay, continuous vector field, okay, continuous vector field on a smooth curve, on a smooth curve, C, given by this equation, R of t equal to the x of t, y of t, z of t. Okay, and of course your t is going to be between A and B. If this is going to be the case, then the line integral, okay, the line integral of that force, okay, along the curve C is going to be defined by the work. E is going to be integral, okay, f dot dr C, which is going to be equal to the integral from A to B. This is the way you're going to evaluate it. It's going to be f of r of t dot r prime of t dt. You have to use a dot product because you have the, okay, both of them are vectors in this case. Or simply, some people like to write it down in this form, integral of f dot dr c is going to be integral from A to B, f dot t. We need this one for, when we get to the interpretation of this integral and those theorems that we're going to have in future. But as you can see, it's the formula over here is almost the same as you did for the scalar value function, but you got to be careful. In the scalar value function, you use the norm of the r prime of t, remember. In a scalar value function, you use the norm of the r prime of t. But in a vector field, it's r prime of t. Make sure you know the difference. Okay, the one that you did before was f of, you see, f of rt. So look at this one. It's f of rt times norm of the r prime of t dt. So this is with the scalar valued, but this is going to be with the, okay, vector valued function. Otherwise, it doesn't make sense when you want to do it. Okay, but otherwise it's going to be a straightforward, okay, function. And we talk about it that this, okay, this quantity over here, remember, this quantity over here also referred to it as a work that's done by moving an object, okay, by the force F. Okay, that's it. Any question? Let's give you one example to see how we're going to find it. This is going to be your next second questions from this section and the chapter for the quiz and the final. Straightforward. Integrations are easy. Mostly people do this one right away. Okay, but some people, they miss this expression. You see, we say find the work. This is the expression. If you check your practice quiz number 4, you will see this expression, find the work done by the field or by the force, field. The force field can be 2-dimensional or 3-dimensional. In this case, the 2-dimensional or the 2 variable. But the important part is the range is a vector. Okay, minus x, y, j. That's your function, the field in moving. Okay, moving a particle object. Moving a particle along, okay, along a part of a circle, along the, okay, quarter circle, quarter of a circle, or quarter circle, r of t equal to cosine of t I plus sine of t j. Since the quarter circle, so t is between 0 and pi r. So, we are mostly interested in 3-dimensional, or 3 variables, but from time to time, you may have it in 2, which is the same, easy to apply. Okay. So the equation of the curve is already given, so nothing to worry about. Okay, already. You go with the formula for the force, for the work. Work is F dot dr on the C is equal to, we change it, it's going to be F of R of T dot differential of the dr would be R prime of T. Then when you're done, D of T. And the T going from 0 to pi half. That's it. That's your formula. Step by step, find it. We find R prime of T first. Then we find F of RT dot product, and then we come back, we integrate it. This is going to be the, okay, the order of the solution. So R of T first, that's the cosine T, sine of T. That's R of T. Differentiate R prime. R prime of T would be negative sine T, cosine T. That's R prime. Find F of RT. F of RT, this is it. So F of the function I write down for you. So F of xy is x squared comma negative xy. Substitute. Find F of RT, F of RT. So we're going to put x equal to the cosine and the y equal to the sine. Okay, so what we have a cosine squared of t comma negative or minus x xy, cosine of t, sine of t. This is f of RT. Okay, go for this one, the dot product. You can do all of them at the same time if you feel comfortable. Dot R prime of T. Make sure don't miss it, it's a dot product. Is a dot product, this is going to be your functions. Okay, the dot product, you multiply them together. So it's going to be cosine square of T times it by negative sine of T plus, okay, plus negative cosine of T sine of T, okay, times that by sine of T, sine T. Okay, just a dot product. Simplify it. So this is going to be equal to negative cosine square of the T sine T, negative cosine of T sine square of T. Okay, so this is going to be the case that we are going to have sine T cosine. Just checking to see if I missed anything. Okay, so that is going to be for the second part. This is cosine T, and then I multiplied by the cosine, sorry, I multiplied by cosine. This is cosine. Okay, because the first, second component is cosine T, and this is cosine. So that gives you cosine square, the sine. Both of them are the same. Okay, the dot product, you see the dot product is this one and this. Now both of them are the same, so you end up with a negative 2 cosine square of the T sine of T. Remember, this must be a scalar, the dot product. Now we are ready to go back and integrate it to get the result. Okay, so the W is the integral of the f dot dr over C. So it's going to be integral from 0 to pi half. 0 to pi half, this is simply the negative 2 cosine square of the T sine of T dt. Okay, everything is ready for your integration. Because you take this one cosine to be u, so the u prime is already here. Okay, so it's simply u square. So it's going to be negative, okay, negative 2 times the cosine cubed of T over 3 to be evaluated from 0 to pi half for that integral. Okay, so if you put the pi half, you get nothing. So there's going to be negative 2/3 cosine cubed of pi half, which is 0. And it's going to be minus a negative 2/3 cosine of 0. So cosine of the pi half is 0, cosine of the 0 is 1. So that gives a negative 2/3. So the answer is 2/3. So the work is going to be 2/3. Depend on the, on the units, then we can, we can evaluate and get the answer. Okay, so as you can see at the end, everything happened to be nicely done. And that's going to be the case. So if you let me do quickly one more with the 3 variables to finish it. Just a straightforward one. And we're done with section 15.2. What we are going to do later, we are going to simplify it. Okay, we are going to simplify it. We relate it to what will happen if this force is going to be conservative. If it's going to be conservative, you are not going to integrate it. You do it in a matter of 2 seconds. Okay, most of the problems. Remember fundamental theorem of calculus. We're going to create a fundamental theorem of calculus over here. If this is going to be conservative, remember this is going to be gradient of a function. That gradient of a potential function would be like the f prime in calculus, okay, function of one variable. So most of the problem of the board can be done straightforward, okay? But let's give you one more example to finish it. Then we do that fundamental theorem of calculus tomorrow. Okay, so you want to evaluate. So we give you one straightforward of this work to create it. You want to find this one where just a three-dimensional one where you have f of x, y, z is equal to the xy times I plus yz times j plus z times xk. And C is going to be a cube given by x equal to t, y equal to the t squared, z equal to the t cubed, and the t between t and 0 and 1. Again, you know, it's straightforward. The evaluation is safe. We don't have anything to worry about. Okay, solution. Again, you know the definition. F dot dr is f of r of t dot r prime of t, then dt. You have to, again, product, you know, find the r prime of t, dot product, and integrate. So we start with the r of t. In vector form is t squared, t cubed. That's r of t. Differentiate r prime of t. 1, 2t, 3t squared. That's r prime of t. Function. Your function is f of x, y, z is what? X times y times z times x. Find f of r of t, replace the x by t, y by t squared, z by t cubed. So f of r of t. Replace it. So what are we going to get? X, y. X is t times y. Y is t squared. That's the first component. YZ. Y is t squared. Z is t cubed. That's the second component. Z. Z is t cubed. Zx. X is t. So what do we have? F of RT, we have t cubed, t to the fifth, t to the fourth. That's f of RT. Question? Get the dot product. So what's going to be f of RT dot r prime of t equal to? This is f of RT and this is r prime. Multiply the coordinates. The first one, t cubed times 1 plus t fifth times 2t plus t to the fourth times 3t squared. Remember, it's a number, it's not a vector. Multiply, integrate. This is going to be t cubed And this is going to be 2t to the 6. And this is going to be 3t to the 6. Okay, 2 to the 6 and 3 to the 6 would be 5. So we get t cubed plus 5t to the 6. That's it. You integrate this one between 0 and 1. And you're done. Any question? So keep it in order. It's a nice one. So f dot dr is t cubed plus 5t to the 6 dt from 0 to 1. If you integrate it, that gives you t to the 4th over 4, 5t to the 7 over 7 from 0 to 1. If you put the 0, we get nothing. If you put the 1, so that gives you a quarter plus 5, 7. Common denominator 28, 7 plus 20. 27 over 28, the final answer. Okay, that's it. That's a line integral. Okay, the line integral on the vector field or on the scalar valued functions. Okay, as I talk about it, what we are going to do tomorrow is we simplify everything we talk about it today. We are going to bring, we have to prove a version of the fundamental theorem of calculus, which is quite interesting from mathematical point of view and from physical point of view, and make things so easy for you to operate. Okay, we do that one tomorrow, and then by Wednesday we get to the best part of this. We do all this, but then we bring a great theorem. We call it Green's theorem. That Green's theorem would be much easier when things getting complicated. Then we can use the Green's theorem. So as you move on, this getting deeper and deeper, but easier and easier, really, and very interesting. Okay, so that's it. If you haven't done your test, good luck with the test. And then if you're missing any class, just make sure to read it quickly. And if you have any question, let me know. Okay, that's it. Have a good one. Take care and see you tomorrow. Bye. Bye. Thank you. Bye.